Hi guys, welcome to another one of my lectures. Today we're going to look at Unit 2 CAPE Module 3 and we'll be talking about the generation of X-rays and we'll be looking at some formulas associated. So in its simplest terms, X-rays are examples of high-frequency electromagnetic radiations and they are basically produced by something called an X-ray tube. Now, in its simplest terms, an X-ray tube is what we call an energy converter. And what it does is that it uses the energy from electrons which are accelerated from the cathode and the anode, which is part of the X-ray tube. Now, in your evacuated chamber, you're going to, in essence, have a filament which we consider to be the cathode, and it's made of a material called tungsten. So due to thermionic emission, when it gets very, very hot, you have a lot of electrons tend to be ejected from this cathode, which is made of a tungsten material. Now you have a metal anode, and the metal anode, we would consider that to have a positive potential. So it causes now an electric field to develop between the cathode and the anode. So when these electrons go to the anode, they become accelerated. There is a particular portion on the surface of the anode called the focal spot, and that is where there is impact between the electrons and the atoms of the anode. Now, when that collision occurs, you have two specific types of X-rays which are emitted. The first one you're going to look at is the continuous X-ray spectrum. So when you have these electrons, right, hitting the specific atoms of the anode, you will find that the attractive force of the nucleus due to atoms in the anode would deflect the electrons and it would tend to slow them down, because you would find that electrons are negative and the nucleus is positive. So that attractive force tends to slow down the electrons, right? So as they slow down, the kinetic energy of the electrons is converted to two things: X-ray radiation and heat energy. And the X-ray radiation is emitted as an X-ray photon. Now the energies of these X-ray photons will vary, and the process is referred to as the Bremsstrahlung process, which means breaking radiation. Right? So now you would have these electrons, as I mentioned just now, slowing down when they meet the positive nucleus of atoms in the anode. And what is dissipated, that difference in energy, is what we consider in the X-ray wavelength. And the X-ray photon, right, as we just looked at the photoelectric effect, the energies of that can be deduced by E is equal to HF, or E is equal to HC over lambda. And the wavelength will be in the X-ray spectrum. Now, the other type of X-ray that is produced is called your line spectrum or your characteristic spectrum. And what it does is that it looks specifically at the shells around the nucleus, right? So let's look at the nucleus here. And then the first shell we have is the K, then we have the L, and then we're going to have the M. So what happens here is when you have an electron which comes in, it basically knocks off a specific electron from the K shell. So now there is a vacancy of a specific electron which is assigned to the K shell. Now, in order to replace it, you're going to take an electron from either the L to the K or the M to the K. And you recall that energies in shells are specific energy levels. So there is a fixed quanta of energy that needs to be emitted when you are going from L to K. And that results in K alpha X-rays being produced. If you're going from M to K, that's K beta, right? So what you will find now is that you have characteristic X-rays which have a specific wavelength. Now, if I were to do a general graph of intensity, which is power per unit area versus wavelength, I am going to get the two kinds of spectrums being produced. Now, this part here is the continuous spectrum, which shows that there is a wide range of wavelength values. At the peaks, you will have K alpha and K beta. And actually, if I wanted to be more specific with my peaks, I'm just going to redraw it here for you. I am going to show it continuous with a range here, and then I have my K beta, and I have my K alpha, and then here I have my L beta and my L alpha. So the peaks, this is K beta, L alpha, L beta. So these peaks are what we call characteristic X-rays, because they talk about fixed energies that are used or produced when it goes from one specific energy level to the other. Now, the two equations that you really have to look at will be the energy due to an X-ray photon, and we are using E is 8c over lambda. And because the electrons can be accelerated, that energy of the photon can be said to come from the increase in the kinetic energy of the emitted electrons as they accelerate within the X-ray tube. So that is equal to EV, which is also a half mv squared, which is the kinetic energy. So now I could equate these two. So I could say 8c over lambda is EV, right? And I could get lambda from that. Right, so lambda is 8c over EV. Alright, something else I would like to look at is the equation for intensity, because if you look at how X-rays work, it's really an exponential process. So this equation speaks about the intensity of the X-ray when it is incident on different materials. So X-rays are used primarily for medical imaging, and many of the times the X-rays are absorbed by tissue and skin, but is reflected by bone, right? So this represents the intensity, right, after it passes through a certain material of thickness x, and the linear absorption coefficient is mu. So this would actually be per meter. X is the thickness per meter, and I0 represents the initial intensity of the X-ray. Right, so let's look at how we could kind of use these two equations, right? So if you have an X-ray tube, and let's say it's operated at 45 kilovolts, so that is the voltage, and the current flowing through it is equal to 1.5 milliamps. The first thing they could ask you is to get the electrical power. So here the power is equal to IV. So that is 1.5 by 10 to the minus 3 by 4.5 by 10 to the 3. So when you multiply that, you get 67.5 volts. Now, if you are told that you want to get the speed of electrons when they hit the target, then you're probably saying, alright, so if they tell you to get the speed, then you could use the formula a half mv squared is equal to EV. Now remember, the mass of an electron is normally given in your constants, 9.11 by 10 to the minus 31, and E is the charge on an electron, which is 1.6 by 10 to the minus 19 coulombs, right? Okay, so then here you can get V, which is 2eV, the voltage, over the mass, the square root. And when you substitute those values, remember you have V, you will get 1.26 by 10 to the 1.26 by 10 to the 8 meters per second. Lastly, what they can ask you to do is they can calculate the cutoff or the minimum wavelength of the X-rays, right? So then you could use the values of 8c over EV that we discussed before. Remember, H represents Planck's constant, which is 6.63 by 10 to the minus 34. C is 3 by 10 to the 8. E is 1.6 by 10 to the minus 19, and V is your voltage, which is 4.5 by 10 to the minus, no, 10 to the 3. Okay, so when you work out that, then we got the minimum wavelength to be 2.76 by 10 to the minus 11 meters. Guys, I hope this video was useful to you. Please don't forget, I have a textbook out. It's a revision guide and it's very good. It's available at all Muhammad's bookstores. And all of the examples that are in the text mirror past paper questions. So it's worked examples. So once you go through them and you are understanding the logic behind it, you'll be fine to try your past papers on your own. Remember, please tell your friends, subscribe to the channel.